Electron paramagnetic resonance, or EPR, is a magnetic resonance spectroscopic technique used to study species with unpaired electrons, such as transition metal ions, free radicals, point defects in solids, or defects induced by radiation with light or particles. EPR detects the transitions induced by microwave radiation between the energy levels of electron spins in the presence of a static magnetic field, which removes the degeneracy of the spin states. The transition energies are affected by the local environment of the unpaired electrons. Therefore, the EPR spectra can provide structural and chemical information about the paramagnetic species. Our laboratory is equipped with EPR spectrometers working in the microwave frequency bands X at 9.5 GHz and Q at 34 GHz. The EPR spectrometer consists of a source of microwave radiation, a resonant cavity into which the sample is inserted between the poles of the electromagnet that generates the magnetic field, and a detector to measure the microwave signal reflected from the cavity. The microwave frequency is constant while the magnetic field is scanned. The microwave absorption signal is recorded as an EPR spectrum. Depending on the samples and the information required, the experiments can be performed at one or both microwave frequencies at variable low temperature with in situ illumination. EPR is a versatile, non-destructive, highly sensitive analytical method. It can detect concentrations of paramagnetic species as low as 10 to -4%. The samples can be in powder form, single crystals or films, cut to sizes compatible with the quartz EPR tubes. However, the film substrate should have higher electrical resistivity and a very low content of paramagnetic impurities. The EPR characterization of the paramagnetic species involves the determination of their identity, oxidation state, concentration, stability, formation, and evolution. Some species are also used as paramagnetic probes to obtain information about the host material, such as local structure and symmetry, lattice dynamics, the presence of local strains, the degree of lattice disorder, the mechanism of structural and chemical transformations. EPR has a variety of applications in materials science, physics, chemistry, biology, medicine, pharmacology, and environmental science or quality control. Our research topics over the years extend from the size-dependent physical phenomena in nanometric particles, structural phase transitions in ferroelectrics, defects in nanostructure, semiconductor, and insulating materials, materials for radiation detection and conversion, gas sensors, biomedical materials, to the characterization of microfossil samples or the analysis of pigments and materials with cultural heritage significance.
Okay. So now we start effectively our practical session, and before entering the laboratory, I will present you some slides. So I would like to see you the first experimental setup used to observe EPR signals. It was in 1944. So you can make a comparison with this new EPR spectrometer, and this is one of the simplest spectrometers which are used nowadays. So the main parts of this spectrometer are the microwave source. It's here called microwave bridge. Then we have microwave radiation going through a waveguide to the resonant cavity, which is situated in a magnetic field. The signal reflected by the sample in the cavity is measured as an EPR signal, which is amplified. Usually the signal is very weak, and there are some electronic tricks to enhance the signal. One of them is to modulate the magnetic field and to record the absorption spectrum as a first derivative. So the main part of the spectrometer is the resonant cavity. The electromagnetic field in this cavity, coming from the microwaves, is forming standing waves, and you see here the magnetic field and the electric field of the electromagnetic field. In this resonant cavity, samples are here. So this is the best position for the sample. The most important parameter of this resonant cavity is the Q factor. This factor enters the microwave magnetic field intensity. And you see it here with this definition, let's say. You see here the absorption. We call it deep, the deep of the cavity, the absorption in the cavity, which depends on the frequency and on the width. The signal amplitude also depends on the Q factor, on the microwave power, on the modulation amplitude, on the recording time, and also on the filling factor, which depends on the sample volume. So for each sample, you have to optimize the volume. Also, these parameters have to be optimized. You cannot increase them too much. We see here the so-called saturation behavior of the microwave power. And we have to stay in this linear regime. Then you have to be careful with the modulation amplitude. And I will show you in the lab how we can handle all these parameters. Moreover, for higher Q factors, we use low temperature measurements. You see here the cavity, which is placed in a cryostat, for which we need low pressure to keep the cooling gas to the sample at a constant temperature. And I recommend you this book, from which I have extracted some images. There is a chapter written by the EPR division of Bruker. And now I think we are ready to go to the lab. No, sorry, there is one more slide. So here there are some details on the samples we use regarding the sample crystallinity, the quantity we need, about the thin film requirements, And now we are really ready to go to the laboratory. Okay. Okay. So you see we are number 1. Okay, so now you see the Xband spectrometer. And for the electromagnet you just seen, we need some cooling water, and this is the heat exchanger. Here we have the power supply for the electromagnet. This is the spectrometer electronics box, let's say, which commands the microwave bridge, the electromagnet, and all the electronics needed to detect the EPR signal. You see now the microwave bridge, the waveguide, and the resonant cavity. Now we enter the acquisition program. And you see here the sample. And I will stop here. This is the dip of the empty cavity before entering the sample. We have to be very careful to have clean tubes and to do not break the tube by inserting it. So now the dip of the cavity moved. It means the frequency changed. And here you see our setup for low temperature measurements. You see the liquid nitrogen cryos, sorry, the transfer line. So we pump liquid to the cavity, and here we have the pumping unit for the cryostat. So in this moment here, we have a different cavity, as you will see in another movie. We are now going to another spectrometer, which is similar to the one in the slides before. It's the simplest equipment we have. Again, Xband spectrometer with a room temperature cavity. And now we are going the Q-band spectrometer. And you will see here all the procedures to start the experiment. I have to tell you that we cannot show you any experiment in real time because it takes many hours, a normal experiment. There are a lot of waiting times, a lot of trials, and I will tell you one by one what is happening. So here we saw something new, which is a goniometer we use when we rotate samples in the magnetic field. And you see here the waveguide. And here there is a quite big cryostat with an optical window for illumination, for in situ illumination experiments. So the pumping unit for the cryostat. The sapphire sample. So this is the way to mount the sample. There is a quite long holder we have to insert in the cryostat. Again, the cavity dip is moving. The frequency is changing by inserting the sample. And we are doing here some small adjustments of the cavity length. You know, when you change the length of a resonant cavity, you change its resonant frequency. And here it's the procedure to rotate the holder with the sample in the magnetic field. Here there is the setup for in situ illumination. So we have here a UV LED, the optical fiber going inside the sample holder. and I hope you enjoyed the music. Okay, and now we really start to work. So after inserting the sample, the spectrometer was started, and now we start the acquisition program. All the comments I make here, they are remote comments, and there are some delays. But from time to time, I will speed up this video. So we connect now. We start a new experiment. Which is continuous wave EPR. We set parameters to the hardware, and there are some predefined parameters. You see the predefined parameters, produce too much sensitivity. We reduce the gain, and we start now the microwave bridge tuning. This is a procedure to optimize the quality factor of the resonant cavity. It takes some time, and before doing this, you also have to wait for all electronics to stabilize, because all electronics produce some small heatings in the resonant cavity, producing some frequency shifts. You see here in the beginning. This is most evident at the beginning of the experiment. So we are now at the Q-band spectrometer, and here you really start to measure one spectrum after 90 minutes from the spectrometer start. So there are a lot of procedures before recording a reliable spectrum. I will do it faster. So we have to optimize this dip to have it as narrow as possible and as symmetric as possible. And when everything is ready, we will read its value here. For the moment, you see only the magnetic field value in Gauss. I think I can do it even faster. So we are just preparing our spectrometer for best results. You see the Q factor, it's already here. You have here the Tesla meter, which is correcting the in fact, it's a correction of the magnetic field, let's say. So I have set some parameters and I can start the first spectrum. And this one should be optimized. So it's always an interaction with the spectrometer. You never have the situation to just put the sample and just do a measurement. You need several hours to interact with the spectrometer until you get the best results. So you see here, we are looking at the line width. You see here I will just, okay. Here we see the magnetic field value at this point, meaning this G factor has this value for this specific magnetic field position. And also we can measure from peak to peak the distance. This is the line width. And usually the modulation amplitude you have seen before should be around 3 times smaller than the line width. So we have now a second spectrum with smaller modulation amplitude. And we check again the line width. And the G factor. You adjust some parameters again. This is a sample with an organic radical, which is very stable, BDPA, and we use it for magnetic field calibration. It means that this sample is sent by Bruker with a precise G factor, and we measure from time to time to see if there is some experimental shift when measuring the G value of the sample. And we have to correct all the G factors we measure. And with this experiment, I'm doing the so-called saturation behavior, and I will increase microwave power to see how the amplitude of the signal changes. And now I'm comparing. Once we have here 30 dB, here we have 24 dB. This is the attenuation corresponding to different values for the microwave power. So we try to increase the microwave power, and we should see the signal amplitude increasing with the square root of the power value. And this is what we are checking here. We compare the amplitude of the two lines. So I have doubled the first line, and I checking if it's similar to the second one. And I'm continuing increasing the power. And again, comparing with the previous one. You see, I'm doing a calculation on the previous line, and I have to superimpose on the new one, and everything is still okay with the power, and I can do, let's say, reliable experiments now at this power. And I think I can continue a bit here, because we are still checking the line width. The line width shouldn't increase when increasing the power. It's another sign of saturation. So until we have a linear dependence between the amplitude and the square root of power, and the line width is not increasing by increasing the power, we are in a safe, let's say, in a safe regime. And I will go further here, and we pass to another experiment. So it's the second experiment, what is going on when we increase the modulation amplitude. Already you see a big change in the signal shape. So we increased modulation again. And again. I hope you see the colors on the screen. They are not very intense. This is a really distorted signal which should have to avoid. We need to have a quite high modulation amplitude to increase the signal intensity, but we cannot go too much higher. Here it's an example of testing the line shape. We have some tools here. We have here Gaussian and Lorentzian line shapes. We can just superimpose on the experimental spectrum to have a first impression of the EPR line. This is better, you see. And we check again the line width, the G factor. And what I have done now, I have extracted the sample to check the Q factor of the empty cavity. No, not yet. Yeah. Now you have seen the frequency was shifted, and I'm adjusting again the same tuning procedure, and you will see which is the Q factor of the empty cavity. We check it from time to time to be sure the cavity is clean, because EPR is so sensitive, you wouldn't like to have some impurities in the cavity. And also sometime after low temperature measurement, it's possible to have some moisture in the cavity, which is really bad. You see here the new Q factor. It was 2,700 and now it's 4,000 for the empty cavity. Because, just checking. Could go to the end, but it's quite, it's not much left. And then I have another experiment to show you. So I have inserted the single crystal sample, which has on top a thin film of zinc oxide doped with manganese. And I will do some angular variation. Normally we take some more time to record the spectrum, but here they are quite fast and even faster because I have increased the speed. And what do we see here? Okay. So we see, if you remember, the 6 EPR lines from the hyperfine structure of manganese 2 plus ions. But here it seems there is a line which is narrower, and we will look at this one and to try to interpret what is going on. So this is the first spectrum. Then we are optimizing parameters. We are checking the line width to do not have too much modulation amplitude. And we are now increasing the power in order to have a higher intensity. And we will check if it's saturated or not. And if not, we stay on the higher power, of course. So I have increased power 4 times, and I should see an amplitude 2 times higher. And it is indeed. So it's okay to stay at this power and to start the experiments of the angular variation. And here, what am I doing? I'm trying to have a first impression of the line shape of this broad line to see if it's Gaussian or Lorentzian. So these are optimum parameters to start the sample rotation. And to rotate, we have to go back to the tuning mode. We rotate the sample, we tune again, and after that, we measure the spectrum. And we are doing the same for every sample rotation. This is why this experiment is quite long. But we will do it very quick. So the sample was rotated with 10 degrees, and this is the new spectrum. We have another Q value each time. Here it's not so evident that this line moved, so we will rotate further. Anyhow, for a single crystal experiment, you have to rotate at least 90 degrees, and you have to have a step of at least 5 degrees. So there are a lot of experimental points you have to gather, let's say. Otherwise, you cannot obtain a structural model. You need a specific pattern, and you have to rotate according to the known crystal symmetry. If the symmetry is low, you have to rotate maybe 180 degrees, not 90. We observe now a little higher amplitude, but it is just the effect of the Q factor, which is a bit better for this sample position. And we see here that narrow line moved from here to here. So this is the first indication that the narrow line belongs to the substrate, which is a single crystal, while the thin film is a nanostructured material. So in nanostructured materials, you have like a powder spectrum. You shouldn't see the lines moving by rotation. So we are now sure that the manganese 2+ lines are from the film, as they are not moving by rotating the sample. Again, this line is moving. So I have rotated again. We are checking the hyperfine splitting, the centrum of the structure, the G value, and then where is this one going? You see, after 30 degrees of rotation, we move from here to here with the substrate line. Normally we shouldn't care about the substrate line, but now it's just an example of this angular variation measurement and how we differentiate between the signals from the substrate and signals from the thin film. Again, tuning and recording. I started the measurements with the thin film plane parallel to the magnetic field orientation, and now I'm rotating to have the thin film plane perpendicular to the magnetic field orientation. While rotating, we change the Q factor, and also we change the signal to noise ratio, you will see. Still it's quite the same. You see already the Q factor, it's almost 2 times lower than in the beginning. And this is why these lines have smaller amplitude. And we are happy now to see the line from the substrate out of this important region, which represents the signal from the thin film. You see, the signal to noise ratio is lower. And what we are doing to increase the signal to noise ratio, you can do multiple scans. We are looking at the lines, and you see we can increase the number of the scans. And if you remember, if you scan 4 times, you will see an improvement of the signal to noise ratio of 2 times. And you will see this one. And I will do it even faster now, because 4 scans is quite long. You here see the number of the scans. And we compare with the first spectrum. One moment. Okay. So this was, I would like to see again something. Okay. It was too fast here. So we can also export data to be used in further programs. And now the procedure to stop the experiment. We are disconnecting from the hardware. We exit the program, and this was all.
So I think I can start. Hello again at the afternoon session. I apologize, we are 1 hour ahead, and yes, for us it's 4:30. I didn't realize that for you it must have been a shock when I said to meet at after 4 o'clock again. In this part, I will present details and illustrations to the concept introduced in the theory course in the first EPR course. With inspiration from Professor Plavic, I have drawn a flow of an EPR study from experiment to information. When we have a sample, we have to decide what type of experiments to perform on it. To select the microwave frequency band for the measurement, either X or Q or even both. The temperature of measurement, if we want to illuminate it or not, if we want to anneal it or not. And then there are the actual measurements, which are followed by the spectra analysis, which includes also fitting simulation with dedicated software and determination of the spin Hamiltonian parameters. From this information, we find out details about the magnetic interactions and the relaxation processes. And in the end, we get our information about the paramagnetic sensors, the local structure and symmetry, the lattice dynamics, structural and chemical transformations. In the first part of these practical sessions, you were introduced to the instruments and the unfolding of an experiment. So we say that we have covered the first part of the study. I will present some things which will reflect all three other parts of an EPR study. And at the end of the practical session, Another colleague of ours will present examples of spectra fitting and simulation using a quite simple program, which is part of the software package of the spectrometer. And I will start with some tools, let's say. So what we get from the spectra resonance, we measure the resonance fields. And it is a tendency to express the EPR parameters in a magnetic field units in Gauss or millitesla. But you have to be careful when you transform them into megahertz or reciprocal centimeters, because you can find all three types of units used in the literature. So when you transform to and from the magnetic field units, you have to consider also the ratio between the actual G value of your system and the free electron G value. And at the bottom of the page, this is the main formula that you use when analyzing an EPR spectrum. This is, let's say, the basic tool. So from the resonance condition, you determine the G values, and you see how it just relates with the frequency and the resonance field. So besides reading the resonance field, when you have an EPR spectrum, you look also at the line shape, and you get some information from the line itself. You measure the peak-to-peak line width, because this gives you information about the relaxation process, and the amplitude of the line, but you also calculate the line intensity either by double integration. So because the intensity is the area below the absorption curve, or just using an approximate formula. The intensity of the EPR spectrum is proportional with the number of paramagnetic centers or of electron spins, unpaired electron spins in the measured sample. The line shape can be Lorentzian, Gaussian, or Voigtian. Now, if you have a spectrum, what information you can get from it? And here it is a simulation of the spectrum of manganese 2+, because you have hyperfine and you also have zero field splitting in it. And so let's say this is a spectrum measured along a random direction on a single crystal. And you look, of course, at the line position, at the resonance field, and you look at the number of lines and the groups which have similar intensity and similar distance between the line and line width. So first, you look at the center of gravity of the spectrum, and here you get an effective G value, and this relates with the electron-Zeeman interaction. And then you look here and see that you have 6 lines of equal intensity and separation and line width. And this shows that it's a hyperfine structure, yes, for the spin 5/2. And the separation between the line, it is an effective hyperfine parameter. And then we looked at, we have 5 groups of lines at equal distance, and this is the 2s fine structure from zero field splitting, the distance between the line. It's also an effective parameter which depends on the orientation with respect to the magnetic field. And here we have our spin Hamiltonian parameter. But then we also look at the properties of the lines themselves. So the peak-to-peak line width for relaxation, the amplitude ratios, because this gives us an idea of strain effects. And we can do also calculation of the spectrum intensity by double integrating it to have something proportional with a quantity which is proportional with the number of spins in the sample. This is an illustration of the effect of the relaxation on the EPR spectrum. So we have a manganese spectrum measured at room temperature. You see that there are very broad lines. And this is the same spectrum measured at 20 Kelvin. And you can look at the difference in the line width. The manganese is in lead wolframate single crystal, and it is less than 0.1%. So it is magnetically diluted system, and therefore the main relaxation or the main broadening mechanism evidenced in the line is from the spin lattice relaxation, which depends on the temperature. So you see how the very broad lines from the room temperature get very narrow at low temperature. And yes, this spectrum was recorded at very low power because it could saturate very easily. Now, another illustration of using different microwave frequencies for analyzing a sample, so-called multi-frequency experiments. Why do you need to do them? So I chose W band because it has a frequency 10 times that one from the Xband, and this is one of the first reasons, the magnetic field resolution. So these spectra are have the same G value, and the field range, it's the same in both graphics, 40 millitesla. And you can see that if the line is a little bit broader in the Xband, you wouldn't see the two different spectra when you have these G values. While you have quite a considerable distance between the lines in the W band. Therefore, you can identify and distinguish centers which have very close G values. It's important when you have many radicals in your sample, many types of radicals in your sample. The second reason, here there is a simulation of the spectrum of a vanadil ion in lead zirconate titanate, and in the Xband, so this ion consists of vanadium 4+ ion and an oxygen 2- ion, and vanadium 4+ is a 3d1 ion, 3d1 configuration. The spin is therefore 1/2 the electron spin, and the nuclear spin is 7/2. So you will have a hyperfine structure of 2i + 1, so of 8 lines. And for the spectrum measured in Xband, where you have both G and so both the electron Zeeman and hyperfine anisotropy. So the G is axial and as well, and also axial is the hyperfine. You see that the spectrum is quite complicated, that the hyperfine structure from the perpendicular from the parallel line is overlapping the one from the perpendicular line. So as I mentioned in the course, when you have in a powder spectrum, the parallel component is the one with the lower intensity and the perpendicular one is the one with the higher intensity, because there are more contributions to the perpendicular part. And if we go to the W band spectrum, you see a very nicely separated spectrum. So you have the 8 lines of the parallel component and the 8 lines of the perpendicular component. And the third reason, if we look at the relative magnitude of the spin Hamiltonian terms, in this case, the zero field splitting and the Zeeman term, or to continue the idea from the course, to look at the relative magnitude of the zero field splitting parameter D with respect to the microwave energy. And for a spin 5/2, like in the case of iron 3+ ions, you expect, if you are in the situation where the D value is much smaller than the microwave energy, you expect to have 5 lines, and you have them in W band, and you have them also in X band for a moderate value of the D parameter. But as the value of the D parameter increases, you see that the spectrum in the X band changes quite a lot. New transitions appear and they are moving, and they are found at some weird positions. While in the W band, you can still have a reasonable 5-line spectrum up to the value of 3 gigahertz, and even at for larger D values, the spectrum still is much easier to interpret than in the X band. Now I will turn to the hyperfine interaction. In the course, I have presented the situations for interaction with a single nucleus. Here are some examples of coupling with several identical nuclei. So when the electron spin interacts with the nuclear spin of n similar nuclei, the EPR spectrum consists of 2ni+1 lines. So for 2 nuclei with spin 1/2, there are 3 lines. For 3 nuclei of the same kind, there are 4 lines. The intensity ratio in the spectrum follows the Pascal triangle rule for this spin 1/2. So here it is the number of nuclei, and this is the nuclear spin. And the succeeding rows are generated by adding 2i+1 numbers, in this case 2 numbers. So for one nucleus, there are 2 lines with the same intensity. For 2 nuclei, there are 3 lines with relative intensity 1, 2, 1. For 3 nuclei, there are 4 lines with a relative intensity 1, 3, 3, 1. And the same rules can be applied for nuclear spin with higher value. So for nuclear spin of 1, if we have 2 nuclei, we have 5 lines, and then we have 7 lines for 3 nuclei. And the corresponding table is generated by adding 3 numbers this time, so 2i plus 1. So for 1 nucleus, there are 3 lines with equal intensity. For 2 nuclei, there are 5 lines, 1, 2, 3, 2, 1, the intensity ratio. And for 3 nuclei, there are 7 lines with this respective intensity ratio. And when we have a more complicated situation where the electron interacts with 2 different nuclei, and so with different nuclear spin and also with different hyperfine coupling. When we have a spin 3/2, so we expect a hyperfine structure of 4 lines. And as you can see here, in the simulation, it was considered that the hyperfine parameter for this nucleus was larger than for the second nucleus with spin 1. So the 4 lines resulted from the 3/2 nucleus are split by the interaction with the second nucleus, which has a smaller hyperfine parameter. Such a situation you encounter where you have the interaction with the central ion, which could be a copper in this case for this spin 3/2. And then you have super hyperfine interaction with a ligand, and this could be a nitrogen ion. And for the same nuclei and with the same hyperfine parameters, this is how the spectrum looks if there are 2 ligand ions contributing to the hyperfine structure. So it is much complicated, and you have to look very carefully at all the periodicities to identify which line is due to each hyperfine splitting, and to really separate the contributions from the 3 nuclei. It is very good then to know what you have in your sample. But as you have seen in the presentation of the applications of EPR, quite often we meet unexpected paramagnetic centers in the samples, which for other methods would not be a problem because they are in concentrations of the order of lower than hundreds of ppms, but they can give quite an important contribution in an EPR spectrum. Now I imported the roadmaps represented for the hyperfine interaction and for zero field splitting. So in both cases, in this case, the Zeeman interaction also is anisotropy. So G is a tensor. It has also axial symmetry. And as you can see, the 4 lines resulted from the hyperfine structure evolve also along sinusoids. Each line is characterized by an MI value from minus 3/2 to plus 3/2. Yes, so the MI values for the nuclear spin 3/2. And for the zero field splitting, I didn't add an anisotropic G factor. If the G factor would be anisotropic, you can imagine that you will have somewhere here the G perpendicular and here the G parallel, or otherwise, it depends which one is larger. And you just have to drag the end of the spectrum and see how it will curve differently. But the idea is that for the zero field splitting, where you have only the selection rules for MS plus minus the variation in MS plus minus 1, the 3 lines evolve differently, so they intersect close to an angle which is called the magic angle of about 54 degrees from the parallel direction. And why I show you this? Because in the next slide, I will show you the angular dependence for manganese, which has both zero field splitting and hyperfine interaction in the lead wolframite and lead tungstate. Sorry, let's not speak Romanian. And it is a tetragonal system, so it has the tetragonal axis C or 0, 0, 1. And this is a roadmap measured in the plane perpendicular to the tetragonal axis, and you see that the variation is very small. If it would have had only the D parameters as I had defined them in the course, these lines shouldn't have varied at all. But there are also higher order terms which affect the spectrum. But anyway, this is the so-called isotropic part in the perpendicular plane. In the parallel plane, we see something very different from the not parallel plane. Let's say it is a variation from the parallel direction to the perpendicular direction. So this variation of the centers of the lines of the spectra are still present here, are quite different from the road maps that I presented you earlier. And this is because the hyperfine and the zero field splitting parameters have very close values. So to identify which is each, if the spectrum itself wouldn't be here, you'd know that the hyperfine lines do not, from the same hyperfine structure, do not interact. So you look at the lines which go parallel with each other. So you look at 6 lines which go parallel with each other, and this is one group of lines. And the intersection of the lines comes from the zero field splitting. And you can, so yeah, this is just a first idea how to look at a complicated roadmap. But if you look at the spectrum, I recalled the spectrum from the relaxation part. You have as a rule of thumb that the hyperfine interaction provides a hyperfine structure of lines of similar intensity and separated by the same distance. So When you have this complicated spectrum, you look at the lines which have the same intensity, and you start from the outer part of the spectrum and you look 1, 2, 3. Here it will be somewhere somehow overlapped. So it will be 4 and 5 and 6. And then you have this 6th line, which would correspond to one of the groups separated by the zero field splitting. If you remember the first spectrum of manganese that I showed you, where I demonstrated how you collect the data for the EPR analysis. And then you separate in the same way the other most exterior group, which correspond to MS transitions. So here it is from -5 halves to -3 halves, and here you will have from plus 5 halves to plus 3 halves. And so you identify those 6 hyperfine lines based on their intensity. So even for very complicated spectra, you just have to follow some rules and work a lot. Or if you have some idea about your system, you can just try with some simulations and hope to be lucky. And I forgot to tell you that I would take questions. If you have any questions, please ask them during the presentation, because it's really a jump between subjects, and it may be very complicated to ask them at the final of the finish of the presentation. So if you want to know anything, just ask me, please, and not on chat. Here I intended to show you how you perform an EPR study from beginning to finish. So I took copper 2+ ions, copper 2+ ion in a single crystal, and it is in a concentration low enough to not have strong dipolar interactions between ions, so it's a magnetically diluted system. And the copper ion can be inserted into the lattice in 3 different sites. So this single crystal has a zinc 2+ position coordinated by 4 chlorine ions, and there are 2 different rubidium positions with different coordination. And this localization would give very different EPR spectra. And moreover, as a single crystal, the single crystal has this spatial symmetry, and it has 4 formula units, and which are related by symmetry elements. And the single crystal spectra are very complicated. So while the powder spectrum would not be affected by these symmetry operations present, or symmetry elements from the crystal, in a single crystal spectrum, we can see, as it is represented here, we can see magnetically inequivalent sites, which are related by a symmetry element. But then for specific orientation of the crystal in the magnetic field, the sites would see a different local field. And if we look at the corresponding roadmap, you see that these magnetically inequivalent centers are separated only in the BC plane, and in the other two planes they are superposed. Now let's look again at this spectrum. So it's measured at 62 Kelvin, and I can say, but I decided not to show that these lines broaden very much as the temperature is increased, and they completely disappear at 150 Kelvin. And if you look at them, you see that they drop here very fast, and this is a Gaussian line. These are Gaussian lines, and as I told you in the course, the Gaussian line shape means inhomogeneous broadening. And let's look at the system, and the copper 2+ has two isotopes with 3/2 nuclear spin and in different natural abundances, but they have different magnetic moments. So their spectra would be slightly shifted one from the other. And more than this, they should be coordinated by chlorine ions, which also have the chlorine also has two isotopes with spins 3/2, and therefore this Gaussian line without the hyperfine of the copper evident on them. So this Gaussian broadening is due to unresolved hyperfine structures. Well, in the case of the second center here, you can say that the hyperfine line is partly resolved, and you can guess, as it is here, where the lines, each hyperfine line should lie. This is what it's represented in this roadmap. And when we went to very low to lower temperature and on certain directions, we are lucky to get a super hyperfine splitting, and it could be determined that it resulted from the super hyperfine interactions with 4 nuclei with spin 3/2. That means that it is an interaction with 4 chlorine ions. And this resolves our question where the copper 2+ ion enters the crystal, and it is in the zinc site. So we have determined the EPR parameters, and so there is a rhombic symmetry. You see that there are different values for the main values of the G and hyperfine parameters, and they have the same orientation, happily, but these direction cosines are the direction define the direction of the tensor axis with respect to the crystal axis. So this is the conclusion of this study, but then we can confirm that this localization of the copper ion by making a simple model of the copper behavior in the zinc 2+ site. So zinc 2+ site has tetrahedral symmetry, and if we look at the effect of the crystal field on the energy levels of the 3D9 system, now copper 2+ is a 3D9 system, and what we actually work with here, it is an unpaired whole. To make things simpler in the interpretation of the copper 2+ spectra, and this is for all coppers that you happen to measure by EPR. You work with the unpaired hole, so you have a system, a spin of 1/2. And so we consider what happens with the energy levels of the unpaired hole in a field with tetrahedral symmetry. And this is done in the point charge approximation. So the ligands are considered, or in this case, the chlorine minus ions are considered as point charges, which have the same symmetry as the site symmetry of zinc 2+. So the free ion has degenerate the orbitals and energy levels associated with the orbitals. And in a tetrahedral field, the degeneracy is partially removed. We have a triplet and a doublet. And as we found out, the symmetry is lower still than tetrahedral. This is for an axial perturbation, a tetragonal perturbation of the tetrahedron. And you see that again, the sum of the degeneracy is removed, and the spin-orbit coupling removes all degeneracy. Now, this is the system of the energy levels system, which we will use for determining the EPR parameters. And these are the G parallel and perpendicular determined for a tetragonal distortion of the copper 2+ site. And this is an example of use of the formula from the theoretical course to see how the spin-orbit coupling mixes excited states in the ground state. And you can compare the values obtained for G parallel and G perpendicular with the values, the experimental values determined previously, and see if the model holds. And well, you may wonder where do we get the energies, and actually the difference, these energy differences can be measured by optical absorption. So they are found in an optical spectrum as DD transitions. So you can have, well, it is a primitive calculus because it doesn't include the covalency and the localization of the electron towards the ligands. Yes, you have here an example of the schematics of the d orbitals, which also shows the reasons for the anisotropies. So you can compare your theoretical model with the parameters previously found and decide if the proposed localization is correct or not, or if you make a more complicated calculus, including the molecular orbitals, you can use that comparison to determine the degree of covalency and the admixture of ligand orbitals in the ground state. So this is an example of how you can get information about the ground state wave function. And the result of all this work is a model for the copper 2+ paramagnetic center in the single crystal. So from a single crystal study, we can also ascertain the orientation of the paramagnetic center axis, which are in blue, with respect to the crystal axis, which are in yellow. But more often than not, we get only powders. So very rarely we get a single crystal large enough to do such a study on it. And this is an example of a powder system containing copper in an octahedral symmetry. So the copper is coordinated in the equatorial plane by 4 nitrogens, and it has 2 oxygens along this axis. And the experimental spectrum is this black one, and this is a simulation of the spectrum. And what we could determine from the spectra were the G parallel and G perpendicular values. So it seems not enough information. We don't have a resolved hyperfine structure, and this is not because the lines are too broad, but because there is a very strong exchange interaction between the magnetic ions in this powder. There is also a chromium ion, and and the other copper ions are at close distance. What we would have liked to get at least would be such a spectrum, yes, with resolved hyperfine structure, but well, we were not so lucky this time. But we have these 2 G values, and we look at the copper ion in an octahedral symmetry, and we have again the splitting of the orbit of the energy levels of the d orbitals in the crystal field, on the octahedral crystal field with a tetragonal distortion. And depending on the relative values of the G parallel and G perpendicular parameters, if you remember the previous formula, they depend on the ground state and the excited state. So depending on their relative values, you can at least say which is the ground state, which what is the wave function of the ground state. And this wave function corresponds to an elongated octahedron. If it would be a compressed octahedron, we'll have an inversion of the energy levels here. So it depends on it really depends on what system you are studying and what form it takes to extract as much information as you need from your EPR spectra. And now I would pass well, how do you say it? I will let my other colleague take the speaker place, but maybe if you want, we can take a break before this last part of the practice session, or we can start immediately, as you like.
So, good afternoon. I don't know if you can see me. But I hope you're hearing me.
Yes, we hear you. I don't see you.
Okay, so I don't know exactly what it's wrong because here it's telling me that my video is working. Looks like not. Anyway, I suppose it's not that important. So good afternoon again. My name is Alexandra Joița and I'm working in the EPR group at National Institute of Material Physics. And today I will present you how we are simulating some of our recorded EPR spectra using a program included in the software package of the spectrometer. And let me discover how to share my screen. 1 second. Okay, so it's something is not working properly here. Okay. Maybe now you can see my.
Yes.
Okay, so I suppose it's in a. You can see all of it, right?
Yes.
Okay, perfect. So I will start with the first example. The first example that I will show you today, it's a EPR spectrum, a powder EPR spectrum of synthetic melanin. So melanin is a stable radical. And the spectrum is recorded in the X band. You may see the value of the magnetic field here above the red line. I hope you can see it. You are seeing here only a single line. So we have isotopic center with an electron spin 1/2. And you may see that the line looks symmetrical. So we will start our simulation by starting the small program included here, and we will add one center. And as you may see here in the window of the program, you can use one or more species and also the nuclei part. And you may change the number of spins, the shape of the line. One represent the Gaussian line and the 0 the Lorentzian part. You may also use a fraction between 0 and 1 to represent the mixture between lines. And you have to complete with your specific values the G factor values and the values of the line width measured from peak to peak, as you will see in this short movie. So we are seeing here when we are measuring. So we are measuring the value of the G factor at the middle of the line, and we will see it here in the program. And if you see some delays in the measuring process, is because I worked remote on this computer from the lab computer, and we still have some internet connection problems. And when we hit the fit button after we put our values, we may observe that we have a good simulation, almost good. So we need to change the shape of the line first. And after that, we will optimize our parameters. So we will check all the boxes to be green. And in the end, we have our simulation, which is pretty good for a first fit of our spectrum, or our experimental spectrum. The next example, the second one, it's the EPR spectrum of the same sample, synthetic melanin, but this time record it in the Q band. You may see here the value of the magnetic field. Okay, so you may see here the value of the magnetic field. And now if you're looking at the line, you will observe that it's not symmetrical anymore. We have a bump in the right part of the spectrum. So this is telling us that we have that we don't have only one center here, we have another one. And we can observe this in the Q band because we have a better resolution of the magnetic field. It was what Mariana was presented earlier. So we will start our simulation using this time 2 species, and we will set our values for the G factor and for the line width. So in this case, the G values and the line width values are chosen as a result of some previous measurements that I've done. So we will complete all of them. So we can say that at the beginning in the Xband, when we suppose that we have only one center, it was just an assumption. And after completing everything, we will fit the result, and it's almost a good simulation. We will check all the boxes to optimize all of our parameters. And in the end, after a little bit longer, so you observe that the time to process the information, it's a little bit longer now that that already has two centers. So this is our final result, which is very good. And it was I will continue with another example. This is an EPR spectrum of a cubic boron nitride, a crystalline superabrasive powder. You already seen it in Dana's presentation earlier today. You've seen also pictures with it. So you observe here that we have two different lines. So we already start our simulation using 2 centers. We are repeating the same steps, measuring the G value and the line width, peak to peak. So we are observe here the line width as well as the G value. We will proceed in the same way for the narrow line. So you may observe that the simulation is almost good. All we have to do is to optimize our parameters, and I will check all the boxes here and try to optimize all at once to see if it's work. it will take a little bit longer. So, and this is it. Seems like we have a pretty good fit of our experimental spectrum. The next example, it will be the EPR sample of the same investigated cubic boron nitride, but investigated in the same conditions, but after an annealing treatment. So here in this new EPR spectrum, okay, so I will go a little bit faster on this part to choose the right. Okay. So you may observe here the new spectrum of our sample after the annealing treatment. So you will observe here that the intensity of the line it's less than before. So this is telling us that our defect in this case is less stable than the other one. So using the annealing treatment, we may check the stability of the defects and we can distinguish between defects. For our simulation, we will proceed in the same way. So we will measure the important parameters and we will put our values in the right positions. So you may observe from this spectrum that the centers have different behavior with the annealing treatment. I will go a little bit further because you already seen how we do the same part. And we will optimize all the parameters at once. An observation, it will be the fact that sometimes the experimental spectrum, the simulated spectrum, it will be in a very good fit with the experimental one, but the values will be wrong without physical meaning. So it is a very important step, that one, to check that the values of the parameters are saying the right thing, because sometimes the program is trying to adjust and it's adjusting too much. So this is taking a little bit longer. So we're still waiting. So we have a good fit, but you may observe that it could be improved a little bit more, but for the moment it's good enough. Next, I will present you the spectrum of manganese in calcium oxide. This one, it's recorded in the W band. You may observe here the value of the magnetic field that is 10 times higher than the X band. And you may see the beautiful 6 lines of manganese that you've seen it a lot this afternoon. And we will start our simulation by changing the spin number with the right values. And for our first try in this simulation, we will choose the G value very close to the G value of the free electron. Here you're not seeing the measurements done on the lined width, but it's something that I already done before recording this. And here it's the first example where we are using the nuclear part. So we've put the right number of the nuclear spin, and we measure the distance between lines and complete the numbers for the hyperfine splitting. And we will try to fit it, and we will see that it's not working, because here in the population window, let me go back a little bit more. So here in the population window, it's 0. So the program is not doing anything. This could be a very good indicator on the fact that we hit a local minimum in the program, and we have to do some drastic changes with one of the parameters to be able to move from that local minimum point. So I will put a number of population here, and I will show you what is happening after. So I will press show, and you will see the lines from the simulation, but you may observe here a drift of the G value. So we will set the G value measured at the middle of the spectrum. So it's measured around here. And we will observe that lines are in position now. And we will try to optimize all our parameters at once. And in the end, we have almost good simulation. For this simple program, it's a very good simulation. And the last example that I will show you it's a spectrum of chromium in magnesium oxide. In nature, chromium has 4 stable isotopes, 3 of them with nuclear spin 0, and 1 with nuclear spin 3/2, and a natural abundance of 9.5%. So we will start our, you may see the spectrum here now. This is recorded in the Q-band. So we will start our simulation using 3 centers, one corresponding to this line at the low magnetic field, and the other 2 centers corresponding to the intense line, one center without the nuclear spin, so with the nuclear spin 0, and the other one with nuclear spin 3/2. So what I'm doing here, it's again the same procedure of measuring the G values corresponding to each line and complete the parameters. So I think we can go a little bit faster here. And now I will use, okay. So I will measure the G factor and the line width, and also I will change the spin number in correspondingly to our center. Okay, so I think we can skip a little bit this steps. And now the last center has the same G value and line width as the previous one, but I add the nuclear spin, and also I've measured the hyperfine splitting. The delays are because of the remote operations. Usually it's working much better than this. And in the end, we will optimize all the parameters. So you see the first fit with all the values that I insert. And now I will try to optimize all the parameters. And after we press the fit button, we have to wait. And with this simulation, I realized that the time it's increased too much. The time when the program is trying to optimize all the parameters at once. So after a while, I decided to stop the operation using this button here, and try again. This time optimize less parameters at once. So I started with groups of parameters, and you may observe that the simulation starts to look very well with looks like the experimental spectrum. And in the end, we obtain something like this, which is a pretty good simulation. you may observe that the parameters can be a little bit more adjusted, but in the end, it is a good fit. So this program, it's very good to be used as a first fit of an experimental spectrum. So this is something that we're doing at the end of some of our experiments. Thank you for your attention.